Greetings, friends. We're going to be talking about equivalent fractions. Whee! Equivalent fractions is what we're going to be talking about, and I can play with this thing all day long. Okay, but I won't. Equivalent fractions. If we got a fraction like 4 over, I don't know, how about 26? If you're looking to make an equivalent fraction, most of us would know, oh yeah, divide each, the top and bottom, by 2. And then we would have 2/13. Another way to approach this would be to write the prime factorization of each number. So maybe you would need to go off to the side and create the factor tree for each. Well, that was easy. And for 26, you've got 2 and 13. Sweet. The prime factorization for 4, the numerator in this case, is 2 times 2. The prime factorization for the denominator is 2 times 13. And if you notice, you have a 2 on the top and bottom. If that's ever the case, you can divide those. 2 divided by 2 is 1, and 2 divided by 2 is 1. So on the top, what you have is 1 times 2, which is 2. And on the bottom, you have 1 times 13, for 13. That's it. That's how you produce equivalent fractions. Let's do another example. How about this one? 21 over 48, or 21/48. Let's write the prime factorization of each. Okay, so 21 is really just 3 times 7, and 48. 48 could be represented as 2 with a 24. 2 is prime, and 24 can further be split into 2 times 12. 2 is prime, and then 12 can be split into, what is it, a 2 and a 6, and 6 can further be split into 2 times 3. So here we have it. On the bottom, in the numerator, we have 2 times 2 times 2 times 2 times 3. If there's anything common in the top and the bottom, we can divide them, leaving 1s. So on the top, we have 1 times 7 for 7, and on the bottom, we have 2 times 2 times 2 times 2 for 16. Simple enough. Nothing changes when you incorporate variables, nothing. So let's show an example that has variables in it. Here we go. I found one. Let's split 10 into a product of its prime factors, which is just 2 times 5. So the numerator becomes 2 times 5. It also has an x that's multiplying and a y. How about the denominator? 15. Prime factorization, a 3 and a 5. 3 times 5. But the denominator also has y squared, which is nothing but y times y. Sweet. Now we can play the game where if we find the same thing on top and bottom, of course it divides for 1. 5 divided by 5 is 1 up top. 5 divided by 5 is 1 on the bottom. Okay. Anything else match up? Well, we've got this y with this y. You can only match up one thing from the top with its same on the bottom. Alright, so what do we really have? 2 times x is going to be left on top, and on the bottom we have 3 times y. This fraction has been simplified. Okay, well this might be tricky for some of us. What would x's value be in order for these fractions to be equivalent? Well, as you see, the fraction on the left, 5/6, we want that to be equal to something over 24. If we were to change this denominator to 24, we'd have to then be multiplying by 4. Well, if we do something to the bottom, or the denominator, if we did it to the numerator, there wouldn't be any change because we're doing the same thing on top and bottom. So it looks like x should have a value of 20 because 5 times 4 is 20. And if you wanted to check yourself, you could write the prime factorization for each of these numbers in the box and then divide what you could, and you'll probably be remaining with 5/6. You got this.